the last thing that we really kind of looked at was the beginning of talking about formation of ions. And we use the periodic table to justify why certain elements would become a certain charge. Okay? And so we know that elements can react, and reactions are simply this. Something to do with the electrons. The atom will either lose an electron, the atom will accept an electron, or we're going to get to a point where the atom is going to share electrons. But chemical reactions are only movements of electrons. Something to do with the electrons. And so a very simple way to think about it, if an atom becomes positive, it becomes a cation. If it becomes negative, it becomes an anion. It's an imbalance between the number of protons and the number of electrons. And by chance, if you get something positive and negative, what do opposites like to do? Attract. And so one type of bond, one of the three types of bonds that we can have is an attraction of opposite charges, and they will stick like very strong magnets. That's essentially what's going on. Now, we predicted ions and what they can become because every ion is trying to look like what? The noble gases. Now, what does that mean? Every atom wants to have the number of electrons that are in the noble gases because of this. Every shell, every orbital is full. Having completely full electron orbitals is stable. And so when we actually get to the noble gas, we are getting a very stable arrangement of the electrons. And that's what elements tend to react and become. And so we can predict this just upon knowing what group the elements are. And so the halogens, which are the group that starts with fluorine, all react to form a -1 because fluorine has 9. The perfect number of electrons around a nucleus is 10, so I gain 1. Chlorine is 17, starts off with 17. The perfect arrangement is 18 electrons, and so I'm going to gain 1 electron, and so on. And so you don't have to memorize each individual element and what charge it becomes because I can read that off the periodic table. The periodic table can be used for a lot of things, but remember, who are the ones that don't follow the rules? Transition metals. And so transition metals have what are called variable charges, meaning that this group has the possibility of having more than one charge. Also, down in this area, they tend not to behave very nicely, and down way over here, they don't behave nicely. And so they can have multiple charges. So predicting them becomes difficult. What I'm going to have to do is give you a little bit more information when I get to that stage, or I give you an element in those areas. I'll give you a few exceptions in which you can actually predict. There are 2. Now, ions can be atoms themselves, or ions can be molecules, a group of atoms. These ions are called polyatomic. Poly meaning many atoms to put together, and they can have a charge overall. I show you one written out called carbonate. It has a C, it has 3 oxygens all put together, and has a -2 charge as a group. And so there are lots of polyatomic ions that are available. All right, I give you a list here, ignore this list. I give you a list here, ignore this list. Well, not really ignore. Those lists are partial. Okay, because you're going to have a TRQ from CHEM-111 on ions very shortly, if it's not open yet. I went and found everyone in CHEM-111. These are all the ones that are available. I had to use a very small type print, okay, to fit them all on one page. Now, some of these are fine because they come directly from the periodic table, and you don't actually have to memorize them. Some are weird. Okay? There's a charge and a name. I need to know the charge and the name. Now this is where TRQs actually become important, because it's a wonderful way to study them. Okay? And this is shear memorization. In a couple of chapters, I'll teach you how we actually determine some of the charge of the group. Okay? And I'll actually, you'll be responsible for learning how to calculate that. But at this moment in time, like almost everybody in chemistry, there's a little bit of memorization at the beginning. All right? Hold on to this. You'll use this for a while. I just wanted to give it to you because we introduced it here. The ones on the past two slides, if you printed off the notes off of Moodle, are the ones we use most often. But they're not all the ones that we use. Okay. 3 slides. There are anions and cations and ones that we use, and we'll come back to this in just a bit. All right, here is something that would have been nice for you to know before the assignment that you had yesterday, or due for the last chapter. All right, when things become charged. All right, titanium, let me give an example. Titanium has the ability to become charged in 2 different ways. Now, titanium, if I look at it, it's argon. Okay. And the next one would be 4s2 and 3d2. Okay. Titanium can be 2 charges. Titanium 2 plus and titanium 4 plus. Those are the 2 most common charges for titanium. When elements lose electrons, especially in the transition metals, they lose electrons from the highest in value first. You wouldn't have expected this because the way that I write it, 4s is less energy, less energetically favorable. 3d is a higher level. But because of the shape, the S's are easier to get to, and so when I become charged, the titanium 2 plus loses its electrons from the 4th level first, leaving it to look like this. Now, if you got this problem, you had no trouble because titanium plus 4, you take off those 4 electrons, 2 from the D and 2 from the S. You would have got that one right without knowing anything extra. But to get the titanium 2 plus, you have to know that the electrons come from the highest numbered value first. And this is just what we see in real life, how they actually react. And so, probably should have told you that before I gave you questions on that. Yeah, that you would assume that we would do that. That would have been nice. All right. So, strontium. What charge does that become without looking at your sheet? Well, we got to find it. It's right there. How many electrons does that have before it reacts? 38. What is the closest number of perfect around it? 36. To get to 36, what do? Lose 2, and strontium becomes a plus 2. What about sulfur? It's right here. It has 16, right? What is its closest perfect number? 18, right? Argon. So to get to 18, it has to do what? It has to add 2 electrons, which becomes a 2 minus, negative 2. The last one, aluminium, if you're in England. Aluminum, if you're here. What is it going to do? Lose 3. Okay. The alternative is to go up to argon 18. That's to add 6. Always better to lose 3 than to add 6. And so you can predict several of these charges. All right. Remember I gave you this sheet out before? One thing that I would love for you to do is write big arrows over here so that you know the trends, okay? And so we're going to look at ionization energies. Okay, the definition of ionization energy is the energy required to remove an electron. Okay, what does it require energy to remove an electron? The electron's attracted by the nucleus, right? And so the positive and negative like to stick together. But in a chemical reaction, I could take an electron. That's one of the possibilities. And so there's an energy necessary to take an electron away. Now, we just said that calcium or strontium wants to lose 2 electrons. Yes, it'll be more stable when it has 36 electrons, but it does cost some energy to lose the electrons. There's an energy to lose the first electron, called the ionization energy, the first one. And there's an energy that is needed to take the second electron away from any atom. That's called the second ionization energy. What do you think the energy is to remove the third? The third ionization energy. That is great. Okay? And so there are ionization energies, and every atom has a potential ionization energy for as many electrons as you have. So if you have 16 electrons, you potentially have 16 different ionization energies. What do you think happens each time you go one more? So the first ionization energy costs you something. What happens to the second ionization? It should cost you what? More. Because what you've done is you start off with balanced positives and negatives. You steal one. You have the same positives, less negative. The electrons kind of shrink in because they're closer. To take another one, the electrons are closer to the nucleus, so that takes more energy to get them away. And once you take another one away, all the electrons get even closer. And so it's like you're stealing. And the more you steal, the more it costs. Now, the trend I'm going to show you is the first ionization energy. What happens across the periodic table taking electrons away the first time? All right, so what is the trend? As I go from left to right, it costs me more. Okay? And as I go from the bottom to the top, it costs me more. Now, that'll answer the questions on the exam, okay? Knowing that trend. Because I'll give you 4 different atoms, and I'll tell you which one is the least, which one has the most. You should be able to do that using these trends. But let's talk about why. All right, let's think about hydrogen up there. 1 proton, 1 electron. Okay? Proton's holding. It's got 1 electron to watch. Okay? Just 1. You should be have a lot of attention for that 1 little electron, right? Let's talk about cesium on the other hand. Cesium has how many electrons? 55. So, if I were to be a pickpocket, who would I go after? Hydrogen holding onto its 1 little electron? Or cesium that has 55 electrons all over the place? Cesium is much easier to take the electron away because 1, the electrons on the outer edge are further away from the nucleus. So it's easy to take them away. If the electrons are closer to the center, like the hydrogen with 1 electron, it's really close. It's harder to take away. So you can say, in terms of up and down, as I go down, it gets easier because I have a lot more electrons. I can steal them much more easily. All right? Why is it as I go across from left to right, is it more? Okay, remember the size. Remember, potassium was much larger than the krypton. Even though potassium only had 19 electrons and krypton had 36. It's because the effective nuclear charge, more positive charge gets out to krypton, so it can bring the electrons in. Well, if there's more positive attracting those electrons, they're holding tighter. Whereas potassium There's not much positive getting out to the outside. That electron's very far away. It's almost trying to run away already. And if it's very far away from the center, from the nucleus, it's easy to take off. And so, as I go across from left to right, they get smaller. That means the electrons are closer to the nucleus. That means they're harder to take off, or it requires us more energy to take it off. So those are the reasons why this trend exists. Okay? And this is the words of why, what I just described. There are a couple of anomalies, okay, in terms of the ionization energy trends. Okay? The first one is right here. Okay? First, second, third. All right? Lithium doesn't take very much. Then I follow beryllium, doesn't take that much, but boron is even less. We said the trend is supposed to get more. There's a little tiny drop there because the first two electrons come from the s orbital, okay, and they follow the trend perfectly. When I shift over to the p orbital, the p orbital, the electron's a little bit farther away, so the first one actually is just a little bit easier to take, but then the trend continues, okay? There's a second issue right here, okay? When I get to the p, this is boron, then I've got carbon, then I have nitrogen, and then the next one is oxygen. Oxygen's a little bit easier to take off. All right, why is that? Oxygen has 3 electrons in the p plus 1 more. So one of them are doubled up. Okay? And so by taking away that, remember, a half full shell is really nice. It's a little bit easier to take one that's already doubled up because there's a little bit of repulsion. And so I'm a little bit off at that point in time. But the trend in general works pretty well across the board. All right. I want to show you something. The trend. What did I not show you on this periodic table? Transition metals. The transition metals are so weird that I even took them off because it would confuse you. So transition metals are not so good in this trend. The rest of the periodic table is. So if I think about ionization energies here, which one is the easiest to take and which one is the hardest to take? Okay, so the trend said that it goes this direction and that direction. So which ones are furthest to this side right here? Furthest to this side. Sodium and potassium. Now, they are in the same family. So they're at least less than anything else on that chart. But how do I compare those two? Which one has an easier time to have an electron stolen from it? Which one? Potassium, because it has more electrons. So potassium is the easiest. Takes a little bit more energy to get the stop. Potassium, followed by sodium. Okay. So I got that one and that one. As I go in my trend, all right, what would be the next one that I can deal with? Phosphorus, which is here, because I got that one and that one. And then I have what left? Okay, I've got, argon and neon. So argon and neon. Okay, so which one is easier to take an electron from? Argon. And the hardest one to take is neon. Okay? That's the kind of test question I might be able to give to you. Okay. Take a look at this. The trend that I talked to you about, okay, is this first ionization energy alone. Okay? Now, I'm going to talk to you about multiple ionization energies. Okay, so sodium, it doesn't cost very much to take its first electron. About 500 bucks. Okay. What about taking its second electron? A little bit more, doesn't it? Like 9 times as much. Why in the world was the first one easy and the second one really, really hard? Well, look at sodium. Sodium has how many electrons? It has 11, right? And if I take one, how many does it have left? 10. And 10 is what? Perfect. To take the next one, I go from perfect to imperfect. I go past what are called the core electrons. The one electron for sodium is its valence electron. The valence is the ones that react. If you go past that, you are in the core. Trying to take a core electron is very costly because the electrons are arranged in the way that they want to. That's what they tend to go towards. For magnesium, the first and the second are pretty easy, but taking the third, once I start taking core electrons away, that's bad. Now you know what a core electrons are when you write their 4s1. This is sodium. If I write magnesium, neon 4s2, I can take 2 away, 2 of the valence, to take anything else. Has to take from that neon, the core. And as I go through, aluminum, first 3 are good, but taking the next one is core. Silicon, I can potentially take 4 away, but the next one is away from core. All right, we're going to see, though, that when we get in this area, sure, there's a huge raise when I get to the core electrons, but it starts getting costly here to actually take an electron. That's because of another property that elements have, okay? You can get to a place where it does start costing us even to take the first one away. So, below I have 3 elements labeled red, blue, and green. All right? Which one has the largest second ionization energy? Would it be red, blue, or green? The second largest ionization energy. All right, how many people think green has the second largest ionization energy? Nobody? How about blue, second largest? Nobody. How about red, second largest? All right, I got about 50% of hands. And I get the, I'm not too sure, but yes, it is. The red one, its first ionization energy takes its valence electron. To take the second one away, you have to get into core. All right, which one would have the greater third ionization energy? All right, calcium or sulfur? What? What did you say? Calcium, why? Yes, once you take away 2, it's the perfect arrangement. To take the third, you have to take a core electron. That costs us a lot of energy. All right, good. Now, we can see that by writing electron configurations. And so, if by chance I start off with calcium just by itself, calcium is argon. That's 4s2, is it? I hope so. Yes. And the calcium 2 plus just looks like argon. So that's cool. Cobalt. Cobalt's a little bit different. Where's cobalt? There it is. Cobalt is argon, 4s2, 3d. Okay, and then count over 1, 2, 3, 4, 5, 6, 7. That's cobalt itself. If I say cobalt 3, what would its electron configuration look like? What is it? 3d6. I take those 2 electrons away, and then 1 of these. Sulfur, on the other hand, looks like this. neon, oops, plus sulfur is 3s2, 3p, 1, 2, 3, 4. Sulfur 2 minus is neon, 3s2, 3p6, which can be written a different way. It looks like argon. And so sometimes I will lose electrons to become more stable. Sometimes I will gain electrons to become more stable, the perfect number. Sometimes I will lose electrons or protons, not protons, I will always lose electrons, and it doesn't actually end up being a perfect arrangement. This is why the transition metals sometimes do different things, because we're not getting to a very, very stable configuration, like when I get to a full noble gas. And so their energies of stability are very, very close so that it can end up landing in multiple places. All right, size of ions. You have two trends. What happens is this, and you can almost think of it as simply as this in terms of size of ions. If you lose weight, you get what? Smaller. If you gain weight, you get what? Bigger, okay? If you lose more pounds, you get smaller, okay? You lose a little bit of pounds, you get smaller. You lose a lot of pounds, you get smaller. If you gain a pound, you get a little bit bigger. If you gain multiple pounds, you get really bigger. That is exactly the same thing that happens when you lose and gain electrons. Because what's happening is the nucleus never changes. The amount of positive charge never changes. But if you take away electrons, there's less negative, it gets scrunched down. Because the attraction is stronger to each one of the electrons. The effective nuclear charge goes up for every electron. If by chance you add electrons into the mix, the nucleus positive charge never changes, and so the electrons are bigger because there's more and there's less attraction to the nucleus. So the trends go in the same direction as the size, okay? Except you get bigger or smaller depending upon if you lose or gain. And so here, lithium starts off relatively large, and as I go across, it gets smaller. Okay, but look what happens when I lose 1, it gets small. When I lose 2, it gets really small. And when I lose 3, it gets tiny. And so as I lose, I get really, really tiny. All right, as I gain electrons, I get big, okay? And so the trend was as you went this way, you got bigger. And even though this negative charge is big, this 2 negative charge is bigger than a 1 negative charge. And so I tend to get bigger. Okay? You tend to get whichever one, as you go down, they always get bigger because there's just more electrons from the nucleus. So that's no problem. All right, an isoelectronic series. This you have to understand. Has the same number of electrons. Any group of elements that have the same number of electrons are isoelectronic. I will give you an example. Phosphorus, 3 minus. 3 minus. Calcium, 2 plus. Potassium, plus. Chloride, -1. Sulfur, -2. Every one of those, if I look at phosphorus, phosphorus has 15, and I add 3, I have 18 electrons. Calcium started as 20. If I take away 2, I have 18 electrons. Potassium started as 19. If I plus 1, I have 18 electrons. Chloride starts with 17. If I have a minus 1, 18 electrons. Sulfur, 16 plus 2 is 18. That is a series of elements that have the same number of electrons. They are isoelectronic. All right. The easiest way to think about size in an isoelectronic series is this. All right. Going to Weight Watchers. Who gained the most? Who lost the most? The one who gains the most is the biggest. The one who lost the most is the smallest. So in this case, an isoelectronic series would put it this way. This guy is much bigger than, E. This guy is much bigger than that guy, which is much bigger than this one, which is much bigger than this one, which is much bigger than that one. And so that is the best way to look at or think about isoelectronic series in terms of size. The one that has gained more electrons is the biggest. The one that has lost the most electrons is the smallest. Alrighty. Arrange these atoms and ions in order of decreasing size. Okay? So I've got calcium with no charge, calcium with a 2 plus, and magnesium with a 2 plus. All right? So in this case, the element that hasn't lost anything is the biggest. So calcium is the biggest. Then, which one is smaller? Which one is the next smallest one? Calcium plus 2. Okay, and then the smallest is magnesium plus 2, because the trend says as I go down, I get bigger. Okay, and so that's generally, so that's why calcium is huge, is biggest. But then when I start losing weight, or when I start losing electrons, the calcium 2 plus is smaller than its original parent, but magnesium 2 plus is smaller than calcium 2 plus because it is higher in the chart. Okay? Of these at the bottom, sulfur minus 2, sulfur, and oxygen minus 2, which one is the largest one? Okay, the potential is sulfur and oxygen because they gain 2 electrons. So they're bigger. And then if I compare oxygen and sulfur, my trend is as I go down, I get bigger. So the sulfur minus 2 would be the biggest one. Okay. Here's an isoelectronic series. What did I say the trend will be? Which is the biggest? Sulfur 2 minus. And then the next biggest one, fluorine. The next biggest one, calcium, or potassium, has only lost 1. And the smallest one, calcium plus 2, is the smallest one. All right. Ionization energy was the energy that it required to take an electron away. All right? Electron affinity is the exact opposite. It's the amount of energy that is given off when an electron is accepted. So it's the yin and yang. It costs us to take, and for us to get an electron, we could have potentially energy given off. All right? Now, the trend is horrible. But let me show you what we might be talking about. Argon. Argon has a perfect arrangement of elements, right? It's the perfect arrangement. If I gave argon an electron, it has no place to put it. It's got to put it in the next highest level energy. So argon doesn't want to accept an electron because it has no place to put it. And so argon, it doesn't give off energy, it actually costs us energy. So it's a positive number, okay? But, on the other hand, chlorine. Chlorine has 17 electrons. It ends up 3 3s2, 3p5. It's got one extra p. To accept that electron in is wonderful because now chlorine has the perfect number and it becomes more stable and I give off energy. So chlorine gives off lots of energy. So this is the kind of thing that we're talking about. Here's the trend-ish. As you go from left to right, it gets bigger. Okay? There is no perfect trend up and down. There's a little tiny bit of a trend, but it's so little of a trend we don't even talk about it. On this side of the periodic table, on the top of the stair step are the nonmetals. Okay? Nonmetals tend to gain electrons. They like to gain electrons. If you take a look, they need some electrons to get to the perfect level, to get to the perfect number of electrons. On the other hand, the metals tend to lose electrons. They don't want to gain electrons. They want to give them up. And so to accept isn't really great. You don't get a lot of stabilization in the metal side on the left. But on the right, the nonmetals tend to like to attract electrons. Okay? And is this trend perfect? No, not by a long shot. We got some issues right here. All right, to give beryllium or magnesium another electron, beryllium and magnesium have a full S. To throw another electron, I've got to promote that electron into the P. That's higher in energy, so it's not going to be stable for us to take an extra one. That's why we see that dip there. Here, nitrogen has 3 electrons. It's happy. Its P shell is half full. That's a stable area. To throw in the next electron, I've got to start pairing those 2 electrons up. That isn't necessarily energetically favorable. It can happen, but it's not going to be real happy to throw just one more into the mix. If you throw 3 into the mix, it's much happier because I go from a half full to a full, and that gives us more energy. But just that one extra electron, it's not so happy about taking. Okay? All right, another trend, which is a trend that we will use forever. It's going to have ramifications for a lot of things that we talk about from this point on to forever. I referenced electronegativity in Biochem 3. Okay, so this is a trend that you really need to know. Electronegativity is a preference of an atom to attract an electron. Okay, that nucleus and the arrangement of the electrons around that atom, does it want to take an electron or does it not? Some atoms really like to take electrons away from other atoms. Okay, and that means they have very large electronegativities. We can put it on a scale and we can say from left to right, it gets bigger. From bottom to top, it gets bigger. Okay, in this picture, where does it not perfectly work? Where? Transition metals. Although even within the transition metals, this probably has a better trend than anything else, but it's still weird. Remember, transition metals are weird. Do you see a row that is absent on this? Noble gases are not there. Noble gases don't want to attract any more electrons. Okay? And so they're left off this chart completely because they don't want to attract electrons because they got the perfect set. Remember, they're happy. They're at Disneyland. They don't want any more. Okay? The least is cesium. The most is fluorine. Okay? And so the highest element with highest electronegativity is fluorine, and the least is cesium. Francium could have even lower, but francium is not around. It's a radioactive decay product. It isn't, if you take a look at its mass, it's not even around long enough for us to get the real mass because it blinks away so fast. So we leave that one off the periodic table in these trends a lot too. We'll come back and use electronegativity as a justification for a lot of things. Metallic character. Okay, what in the world is a metallic character? It behaves like a metal. You know what a metal is, right? It's shiny. If I hit a piece of metal, does it shatter? No, it bends. That's malleable. If I take a metal and I stretch it, it becomes a wire. That's called ductile. If I take a metal rod and I shove it into that electrical socket, what happens to me? I could die. Or I could get a really good hairstyle. Because the metal does what to electricity? Conducts it. What happens if I put a piece of metal like a wire hanger and I've got my marshmallow on it and I put it in the flame, right? Can I take that and just stick it right in my mouth? You could. And you might do it once. But what happens to that piece of metal when it's in the fire? Conducts heat. Okay? So they're conductors, they're shiny, they have tendencies and properties the same. They tend to become positively charged when they react, meaning they have low ionization energy. Okay? And when they get into water, they tend to become ions, and they form cations. There's a lot of similarities in metals. Metallic character increases from right to left and from top to bottom. Now here's the problem with trends. Okay, if you've been filling out your little chart and writing arrows, okay, it's easy to get the arrows mixed up. Which ones are bigger, which ones are littler. Okay, so that is the only difficulty about this chapter, is to get your arrows straight. As you go down a group, it becomes more metallic. That means it's going to conduct electricity better. It's going to react more for metals. Okay, it becomes more metallic. An area where you can see the trend going down is this column right here, the carbon group. Because carbon at the top is the typical nonmetal. It is a nonmetal, hands down. As you go down, silicon, germanium, tin, and lead, by the time you get down to lead, that is the typical metal. So as I go down a column, it gets more metallic-like. So I can go from the classic nonmetal to a classic metal in one row by itself, in one family. Nonmetals are a whole lot more diverse. There's not much I can say about them that characterizes them all completely. Two things. One, they tend to gain electrons and become anions when they react. Two, they tend to be insulators. They will insulate electricity from flowing, and they will insulate from the heat flowing. So if you cook with a cast iron skillet, you use a cotton, which is made of carbons and hydrogens, potholder to pick that up. Okay. They tend to have various colors. If they are solid, they're brittle, so if I hit it with a hammer, it shatters. But they're kind of varied. Metals and nonmetals, when they react, they form a compound called a salt. What is salt? If I asked what was salt before I showed you this slide, what would you say? Sodium chloride. Sodium is a metal, chloride is a nonmetal. That is a salt. That is called table salt. But any nonmetal and any metal put together is a salt for a chemist. Salts are a lot more varied. All right. Metal oxides tend to be basic if I put them into water. We'll talk about that later. And nonmetal oxides are acidic. We'll talk about that when we get to acids and bases. Metalloids can't make up their mind. The biggest thing about metalloids is they're semiconductors, like semiconductor chips or Silicon Valley. They don't conduct electricity only under certain circumstances. Whereas a nonmetal is an insulator and a metal is a conductor, they are in the middle. They can look like this, shiny, just like a metal, but if you hit it, it shatters just like a ceramic plate. And so they have properties of both. They can't quite understand where they are. The important part is this. Do you see boron? If you start on boron and you draw a stair step from boron down the periodic table, any element that touches it, except for, what's this element right here? Aluminum. Aluminum is definitely a metal. And this element right here is polonium. Any other ones that touch that stair step are the metalloids. And they separate the metals and the nonmetals. Okay? So at this point in time, you can answer every single question on the homework itself.